Hi, AP Physics. It's your teacher, Steven Zawicki. In this problem, I'm going to be describing the uh, way to calculate the total horizontal range of a projectile launched at the same elevation it lands at. The book skipped a couple of steps, and so I wanted to make sure that you fully understood how this sort of problem works. It assumes you know some things that you might not otherwise. I just want to make sure that all of that is clear for you. So the first thing that I'm doing is I'm splitting up our initial velocity into its components. And we can understand a couple of things about our problem here. So the first is that we know the velocity at the apex right here. The velocity at the apex in the vertical direction is 0, right? It is going to go up and then it's going to come back down. And when it switches directions, that's where the velocity is 0. Right? If it still had a positive velocity, it would still be going up. If it had a negative velocity, it would be going down. So at this point, right when it switches directions, it also switches directions with the velocity. So the first thing that we can do is we can write down that the velocity here is equal to the initial velocity minus, actually, the acceleration of gravity g. So we are going to be representing the acceleration of gravity with a g, a lowercase g from now on. And we can substitute in that the velocity at the top is 0, right? And that is equal to the initial velocity sine of theta, since the vertical component is on the opposite side, minus gt. Okay? And we are going to be solving for this time to the apex. So I subtract both sides of vi sine of theta, right? And I'm going to divide by g to get it onto the other side. So it's going to be, and by negative g. So I'm going to get vi sine of theta over g is equal to the time to the apex. This is our first step. In the next step, the book solves for the vertical height that the projectile is able to fly. So we're going to be doing the same thing here, and I'm going to go through a couple of the parts that the book tends to skip. So we want to know the vertical height at the apex, and this is equal to the initial value of height plus the initial vertical velocity times time minus 1/2 acceleration of gravity times time squared. Now we can plug in a couple of things so that y at the apex is the height. We know that the initial vertical height is 0, so I'm just going to leave it out. It's not even there, right? The vertical velocity is equal to vi sine of theta multiplied by the time at the apex. Both of these are time at the apex, so I can just substitute that in. Vi sine of theta over g minus 1/2 g vi sine of theta over g, and this whole thing is squared, right? Okay, so this is where they skip a step and you miss something, so I'm going to go through the specific pieces that get us to the end. So here we have our vi sine of theta, that gives us vi squared sine of theta squared. Over the acceleration of gravity minus 1/2 g vi squared sine of theta squared over g squared, right? Our g's cancel, so we are left with vi squared sine of theta squared over g minus vi squared sine of theta squared over 2g. Now, since this whole thing and these are the same, right? And I just have that 2, so I just have to subtract half that value. So that means that I am then left up with a height equal to vi squared sine of theta squared over 2g. This is our final answer for the vertical height. So finally, all we need to do is find the vertical range. So at the top of the page, I have the x component of our initial velocity and the total time. Notice I've multiplied the time by 2, right? It's only time to the apex before. So, and the time to the apex is symmetrical. So time up is time down. All I got to do is multiply by 2, and then I have it. All right, so let's get started here. So we know that the position and the final position is going to be equal to the initial position in the x plus the x velocity times time. And remember, the acceleration in the horizontal direction is 0, so I don't even include it here. Now, this guy right here is 0, so I don't even include it, right? If I start from 0, that makes things pretty simple, so I don't even have to worry about it. Now I just have to convert my velocity in the x direction initial as vi cosine of theta times 2 vi sine of theta over the acceleration of gravity. Okay, I can combine all of this together, rearrange some things around so that it's vi squared 2 sine of theta cosine of theta over the acceleration of gravity. Now you'll notice that I switched some things around so that all 3 of these values are right next to each other. I've done this strategically because there is an identity called a trig identity. 2 sine of theta cosine of theta is equal to sine of 2 theta, which cleans things up, right? This is technically our final answer over here, but it is a bit messy, right? There's a lot of stuff going on. So let's clean it up. We can use this trig identity and we'll get there. So in the end, the final range, that horizontal range, is equal to vi squared sine of 2 theta over the acceleration of gravity. Using this equation, we can get there. Now, there's an interesting piece about this equation, which is that anything that is symmetric around a 45-degree angle is going to get you the same horizontal range. So if I am at 60 degrees or 30, I'm going to get the same. And that's because you're trading off the different components from one another. So let me draw that a little more clearly here. So if I am launching at 60 degrees, let's say that was 60, okay, right? I have a strong vertical component, and I will have a smaller horizontal component, which means I have a lot of time in the air, but I don't get to go across in the horizontal direction very quickly. So I stay up in the air very long, but I'm not moving very fast. Now I've drawn my 30-degree angle, and notice I get the same horizontal range. Now, of course, I've drawn it to make it look this way, but this is what happens in the real world. Notice my y component is much smaller, right? It doesn't go up as high, and my x component is a much larger portion of the ratio between the two. So now I get to move much faster in the horizontal direction, but I don't have very much time in the air. And so you keep trading these things off, and 45 degrees is that perfect mix between the two. And that's actually going to get you the maximum horizontal range. All right, I hope this was helpful, and I will see you next time, AP Physics.